Maintaining viability in today's economic environment is crucial. To accomplish this, we must continually find new ways to make more efficient use of farm inputs, such as fuels, fertilizers and chemicals. Feed is just one of these costly inputs, whether bought in or grown on the farm, and it must also be used in the most efficient way possible. To do this, it becomes imperative that we understand how feeds are utilized by animals, and how we can use this knowledge to our own economic advantage. This program examines what's perhaps the most neglected aspect in the diet of our farm animals, and that's usable or metabolizable energy. All living things require nourishment in some form or other. Plants get theirs from the soil and the air, fish take theirs from the sea, and parasites from their host. In each case, the nourishment is taken into the body and processed into a form that can be used. With animals, as we all know, this happens through the digestive system, the stomach, and the intestinal tract. But these systems do vary. For example, elephants have a single stomach, pretty much like our own. The food lies around in the stomach for so long that eventually the digestive juices break it down. It's broken down into a form that allows the useful and necessary elements to be drawn out by the body. Cattle, on the other hand, have a system of 4 stomachs. The first is a large fermentation vat called the rumen. This prepares the food to then be digested in the other stomachs, the last of which is similar to our own. Now, the horse has a stomach, much like single-stomach animals. But the food goes into a cecum, an enlarged appendix, where the forage is further broken down for later absorption in the intestine. Then there's the rabbit-type system. Rabbits eat their own manure, or feces. In this way, they recycle the food through their system several times, each time breaking down the forage further and further, until the rabbit system has absorbed the available nourishment. As you can see, there are numerous types of systems at work in the animal world. But no matter what the system, what's common to all animals is that each one draws a variety of different things from their food. And in this series, we'll be looking at what those things are, how they affect growth and productivity, and how we can apply this information to our beef and dairy herds. All cattle require 3 basic components in their forage: energy, protein, and then that group of trace elements, vitamins, and minerals. We'll look at energy levels first, and specifically the energy which can be absorbed and utilized or stored by the animal. All animals require energy for the maintenance of their normal body processes and functions. And then further energy is required to produce milk, wool, and weight gain, as well as to support pregnancy. It's the understanding of these energy needs which is crucial in the selection of a proper feeding pattern for your particular purposes. We must ask what energy levels are available in what foods. How much energy is required for maintenance, and how much is required for production? And how can this information be applied to your needs today, be they dairy or beef? Now, all foods contain energy, but not all of this energy can be extracted by all animals in a form which is beneficial or useful, and each type of animal will be different. Much of this energy can be lost in the feces and urine, or it can be converted to gases. Energy levels in food are measured in different ways. The most commonly used and accepted form in this part of the world is the one which measures how the food is actually absorbed or metabolized by the animal. This system is referred to as the ME system, ME being metabolizable energy. Although there are several systems of measuring energy levels, we'll confine ourselves to the consideration of the ME system. To accurately measure the energy used by animals, scientists make use of metabolism cages, like this one. First, the gross amount of energy in the feed is measured. Then the energy output in the urine and feces are measured and deducted from the animal's intake. Output energy of gas also needs to be deducted. If you fed the same food to a variety of species of ruminant animals, the ME value of the feed will be different for each one. This is because their systems can take varying amounts of energy out of the feed in their particular digestive systems. In fact, ME values will even be slightly different for each breed of beef and each breed of dairy cattle, although this is not a major difference and normally needn't be taken into consideration when calculating feed values. A distinction is made, however, between beef and dairy cattle. A certain amount of energy is required by all animals for maintenance and functions of the body, and this we call maintenance energy. In terms of production, this energy is lost and must be considered an overhead in an animal production system. Any energy in excess of this can then be utilized by the animal for production of either milk or meat, wool and pregnancy, up to the genetic capabilities of the animal. Let's take a look at an example of energy requirements, remembering that we now measure energy in kilojoules rather than calories as we did some years ago. According to this analysis, this average 500 kilogram Holstein Friesian dairy cow needs about 56 megajoules a day just for maintenance. For her to then produce 1 litre of 4% butterfat milk, she needs an additional 5.3 megajoules. So if you want 12 litres a day, she needs another 64 megajoules. That's in addition to the 56 for maintenance, making a total of 120 megajoules a day. With beef cattle, say an average 300 kilogram beast, it needs 40 megajoules a day for maintenance and another 39 megajoules to gain a bit over a kilogram a day, making a total daily requirement of 79 megajoules. If an animal could eat an unlimited amount of food, it would be possible to produce as much as, say, 40 litres of milk a day from a cow eating nothing but wheat straw, if she would keep eating enough wheat straw to consume the required amount of energy. Obviously, that's impossible, as she'd have to eat an enormous amount of dry matter. So, as we can see, the density of energy in the feed is extremely important, particularly with roughages which are relatively dilute or have a low density of energy. There are two factors in the animal which can limit the quantity of food eaten, and these affect the amounts of concentrate and roughage the animal can eat. The first is the acidity level in the rumen, and the other is the volume of the rumen. All food is broken down into volatile fatty acids in the rumen. If an animal ate grain only, which of course is the obvious way to maximize the amount of energy concentration in the animal's feed, this would very rapidly produce a large volume of acid. The first stomach is not designed to handle this excess amount of acid. This excess is then detected by sensors in the animal's stomach, and a signal is sent to the appetite center of the brain, reducing its appetite, and consequently it stops eating. The problem of excess acidity can be overcome to some degree by adding buffers or other chemicals to the feed, which will reduce the amount of acidity in the first stomach. However, ruminants have developed a fermentation system to handle high levels of roughage. So it's imperative that we retain a significant proportion of digestible fibre as found in quality forages in the diet. But forages are generally lower in energy than grains. When eating large amounts of forages with a low density of energy, such as hay, the rumen, or first stomach, becomes full before adequate energy is consumed. Stretch receptors in the lining notice the fullness and again advise the brain appetite center. This reduces the desire to eat any more food and limits the intake of the animal. Under some conditions, dry matter intake can be raised by decreasing the amount of water in the feed. Wilting before storage achieves this, and also decreases the amount of energy or sugars consumed by bacteria in the fermentation process during storage, and so raises the nutritional value. Also, we can increase the amount of dry matter to be consumed by precision chopping the material into lengths of 12 to 18 millimeters. This reduces eating and digestion times and increases the total feed passing through the animal. Another partial solution to increasing intake is to improve the palatability of the feed. If it tastes better, they'll eat more. This is done in silage by the acids produced during fermentation. In the case of harvest or haylage particularly, optimum acid levels can be achieved for even greater palatability. So as you can see, there are a number of ways of achieving this balance between nutritional values and intake capabilities. Now we can go a step further and examine the various sources of nutrients available to cattle. For example, pastures like this, lucerne, provide an increasing level of energy up to an optimum value. In clovers and lucerne, this is usually just before flowering. In grasses, it's just as the flower emerges. After flowering, the energy level drops off rapidly to a very low level as it grows rank. The major problem is that pastures cannot always be grazed at the ideal time, that is when energy levels are highest. And also, the high moisture content in the feed will limit the total dry matter consumed by the animal. So, to take advantage of the peaks of nutritional value in these feeds, we end up with a situation which requires conservation of the fodders. Here the idea is to conserve fodders to retain the energy in the crop at whatever stage it has been harvested. This, of course, would be when the nutritional level is at its highest. This will then be fed out to animals later, having retained the nutritional value during storage. Haymaking allows us to conserve forage by having very low moisture levels. This provides a relatively stable material. But energy is lost during the drying out process itself. The dry and brittle nature of hay allows further loss of nutrition during baling and cutting. However, once made, the material is not susceptible to a large degree of breakdown during storage. The advantage of haymaking is that it's relatively easy to do, although requiring some degree of equipment and feeding out in the paddock. While labour-intensive, it is relatively straightforward. At the other end of the scale, it's possible to make silage from the material by retaining the moisture. This causes it to pack down very well in the storage system and minimises air. The moisture promotes anaerobic bacterial activity. These are bacteria which work in the absence of air. This produces acids and eventually pickles the silage to a relatively stable material. The disadvantage, though, is that large proportions of the metabolizable energy, in this case soluble sugars, are used up by the bacteria in producing these acids which pickle the silage. So, energy levels are never nearly as high as they were in the material when it was initially stored. It's also difficult to have storage systems which totally exclude air, and quite often large areas of waste material result, particularly around the surface of the bunker or pit. And as we can see, the feeding out of silage can be somewhat messy and difficult. Harvest or haylage is another way of conserving fodder. It's a sort of halfway house between hay and silage. It's not dry enough to have the disadvantages of high respiration losses, brittleness and leaf loss, as in the case of hay, and yet it's not so wet as to have the high fermentation levels that occur with silage. Haylage has the added advantage that the undesirable bacteria that are often present in silage do not occur and are unable to survive in the 50% dry matter conditions. Haylage, being light and fluffy, however, cannot be successfully compacted and is susceptible to combustion. Therefore, it must be stored in a harvest or haylage structure. This structure restricts the entry of air during storage and feeding out and provides an oxygen-limited condition. The advantage of haylage material is that it's preserved at a significantly higher nutritional level than either silage or hay. The cost of storage in this system, whilst higher than the others, must be weighed against the greater metabolizable energy and the value of the higher levels of production. As well, dry matter losses are minimised and there's a potential for increased stocking rates. Of course, all these systems depend on good crop and animal management to achieve their potential. Remember, dry matter intake is of crucial importance. Silage is normally made from 20 to 30% dry matter. Hay is made from 80 to 90% dry matter, while haylage is made from between 50 and 55% dry matter. So what we have to consider is a trade-off between the cost of the various conserved forages and their nutritional values and convenience. So far we know that metabolizable energy, or ME, is really just the energy which the animal can take from its feed for maintenance and production. We've also seen that the volume of intake is the most limiting factor in forage, and so we must aim for the greatest intake of food at maximum nutritional levels. However, it might be difficult or even impossible to provide enough ME in forages alone to sustain a particularly high level of production from a particular forage. And that means we have to find supplements like grain or meals to mix with the forage and create a balanced ration of sufficient ME value for our desired production level. Now, these are charts which provide general ME values of cattle forages and concentrates, and similar information should be obtained for your own preparation by having it analysed. It's essential that an accurate ME value of your cattle's ration be calculated to make an accurate judgment. Remember, average values for beef and average values for dairy cattle are adequate for our rationing purposes. These are another set of charts which provide the ME values required by cattle for maintenance and for production. With these figures and the analysis of our forage and supplement samples, we can now determine the ration mix balanced for energy. First, we calculate the total dry matter intake of the animal. Then we use this figure in a formula to calculate the amount of forage required. Then we calculate the amount of supplement to mix with the forage. From this, we can then determine the ration mix balanced for energy. Now, it's not a difficult process to go through, and you can appreciate the importance of a proper and thorough analysis. Now, I'd suggest that you come back to this part of the tape later on to work out the calculations using your figures and find the proper total mix ration for your herd. Success in the beef and dairy business demands an appreciation of many complex factors, not the least of which is the satisfactory nourishment of our herds. The information in this program gives us a basic understanding of the energy needs and requirements of beef and dairy cattle, and we can now make some more scientifically based decisions on future feeding patterns. Additional information on protein and minerals available in the next two tapes will help to expand our knowledge of the nutritional needs of our herds, and we can then apply this to increasing productivity.